rock from the sun. For centuries, we humans have gazed at our neighbor and imagined an alien world. And as human technology advanced and telescopes brought it closer, we began to see signs of life.
As the 20th century began, mainstream credentialed astronomers were looking at Mars, thinking that they saw evidence for a society, a civilization on the red planet.
We Earthlings braced for contact. If there was life on Mars, what form would it take? We set off into space to find out. But as we approached the red planet, we discovered a new mystery.
All the elements needed for life are there. So what happened? Where did everybody go?
Mars is almost Shakespearean, a beguiling world. It's tricking us every way.
So Mars, dead or alive? Some think Mars was home to an ancient civilization.
There was at one time intelligent life on Mars, and they built something.
But the evidence continues to elude us.
If there's life there, we'll find it.
Across the globe, the race is on for the greatest discovery of all. Join skeptics and believers alike as we try to answer the age-old question, is there life on Mars? If you're planning a trip to the planet Mars, here are a few travel tips to help make your journey as comfortable and rewarding as possible. All in all, the expedition will take about 2.5 years, including approximately 12 months aboard your interplanetary spaceship. So make yourself comfortable. Plan your provisions carefully. You'll need to bring plenty of water. At this time, there's no liquid H2O anywhere on the planet's surface. You'll also need an effective spacesuit and a sufficient supply of breathable air. Finally, remember, Mars is about 1.5 times further from the sun than Earth, which makes this a cold world. The temperature can drop to a chilly -130 degrees Fahrenheit. So dress warmly. These technical issues aside, Mars has a lot to offer. It is home to the largest known volcano in our solar system, a magnificent Grand Canyon, and breathtaking deserts. For those of you interested in culture, a visit to the notorious Face is a must. We know you have a choice, so thank you for choosing the planet Mars. All in all, without ever setting foot on Mars, we know a lot about this distant world. But what we don't know is, what about life? When the first astronauts arrive on Mars, who or what will they find? Will aliens be there to greet us? Or is no one there at all? Inquiring minds want to know, is there life on Mars? It's a big question, and a fundamental one. Because really, it's synonymous with the question of, are we alone in the universe?
If we go to Mars and find evidence that there was life on Mars or is life on Mars, then we'd be able to say that in our own solar system, life appeared twice. And I think that would be convincing evidence that the universe is full of life.
Discovering life on Mars could also reveal a lot about our own existence.
We have one kind of life adapted to one planet, even with all of its diversity. So looking at the way other planets may have given rise to a phenomenon that we would recognize as life can enable us to understand our own kind of life in a deep and fundamental way.
The stakes are high in the game of life, and Mars may hold the key.
If we're going to find proof of life on Mars, we're going to have to go to Mars to get it.
But getting to Mars isn't exactly easy. The Apollo astronauts took about 2 days to get to the moon. A journey to Mars one way is roughly 7 months. Mars takes about twice as long to orbit the sun as Earth. So a space mission has to plan departure when the two planets are close. The challenge of bringing a mission back is incalculable in complexity. Just one of the reasons no manned mission has ever been attempted. But that's exactly what Dr. Robert Zubrin of the Mars Society wants to do. Bob Zubrin, an astronautical engineer with 15 years of experience in the space industry, has been planning a trip to Mars for the last 2 decades, and he's come up with a novel way to do it.
If we want to go to Mars, we need to travel light, live off the land.
What makes a Mars mission so prohibitively expensive is the amount of mass, mostly rocket propellant, you have to send there and back. Instead, Dr. Zubrin came up with the following plan. Take supplies enough to get there, then make what you need on the planet.
There's 3 things we want to make on Mars. First, most importantly, propellant. After that, water. And third, oxygen. We can make all 3 with this machine.
Here's how the machine works.
The Martian atmosphere is 95% carbon dioxide gas. We pump that into the reactor. We mix that with a little bit of hydrogen. You can make that reaction produce either methane or carbon monoxide or any mixture of the 2. And water.
The methane and carbon monoxide mixtures can be used as rocket propellants for the return trip to Earth.
The water, we could keep the water and drink it, or we could electrolyze it into hydrogen and oxygen. The oxygen that comes off, we could use as breathing oxygen, we could use as rocket propellant oxygen. That's how the machine works. It makes your fuel, it makes your oxygen, it makes your water.
And leaves enough room on your spaceship for food. All in all, it looks simple enough, and it's not just theory. Working with simulated Martian air, Zubrin has spent years testing and refining the technology.
This is a subscale methane, carbon monoxide, oxygen rocket engine. It all works. It works great. These are great propellants. We start them right up with a spark plug time after time.
In a way, Zubrin has done all this to make a point. Current thinking is that it is too expensive and dangerous to send a manned mission to Mars. Instead, the international space community has deployed a range of unmanned robotic explorers on and around the planet. But Zubrin points out using robots to do field research leaves a lot to be desired.
Okay, we can send robots to Mars, and I support sending robots to Mars. I think we ought to send a lot more robots to Mars. Okay, robots can make all kinds of discoveries. They can give us all kinds of data. They can image the surface of the planet and possibly identify interesting targets for exploration. But they won't tell us the answers that we need to know. They won't tell us if there's life on Mars.
So does Zubrin expect to find life on the red planet?
I think that a naturalistic view of the universe would suggest that the Earth is not special, and that if life can evolve here, it could evolve elsewhere where environmental conditions are similar. And if there's life there, we'll find it.
But perhaps there's an easier way to find out. The answer could already be here on Earth. Every year, hundreds, maybe thousands of aliens come to our planet. Most arrive quietly and go unnoticed. Others enter the atmosphere in a blaze of glory. These aliens are meteorites. For centuries, these rocks from the sky were treated as curiosities, often ending up in local museums or private collections. But the information meteorites contain is so valuable that today, the scientific community sends out search parties to gather them. Although meteorites fall randomly all over the Earth, one of the most popular hunting grounds is Antarctica. Every year, scores of scientists take their lives in their hands and head to the frozen continent. The teams conduct a systematic grid search of the icy landscape, looking for telltale dark shapes against the blue-white of the ice. It was on an expedition such as this that a meteorite was found that would shake the scientific community to the core. The team sent it to a special facility at the Johnson Space Center in Houston, because this is where NASA keeps the aliens. 84001, or the Allen Hills meteorite. The strange green rock was kept under strict quarantine. It was processed, examined, and rigorously interrogated for information about its home world. It took 10 years, but investigators finally got the truth. This rock was from Mars, and it had a secret to tell.
Today, Rock 84001 speaks to us across all those billions of years and millions of miles. It speaks of the possibility of life.
So what was it the rock told us? We'll come back to that a little later. But perhaps the best evidence of life on Mars is not hidden deep in an alien rock. There are some who believe a vital clue is staring us right in the face. Richard Hoagland has dedicated his life to examining imagery transmitted to Earth from various Mars orbiters. Surveillance systems that have circled the red planet for over 30 years now. In the first pictures that the 1976 Viking orbiters sent back from the planet's surface, Hoagland saw something that blew his mind.
I looked at this and it was like, oh my God. This thing had symmetry, it had proportion, it looked like a statue.
Hoagland is referring to this remarkable image, a face-like structure the size of multiple city blocks. And Hoagland thought he saw more. Other structures surrounding the icon, eroded by time. To him, it looked like the ruins of a monumental city.
It looked eerily like an aerial photograph taken flying over Giza, looking down at the pyramids on the Giza Plateau. It looked like a ceremonial complex built by somebody with a huge sphinx-like creature staring up into space from the sands of Mars at the telescope orbiting 1,000 miles overhead. Somebody was down there, and they cared enough to leave the very best.
Needless to say, Hoagland's theory raises more than a few eyebrows. But did life on Mars ever exist? Was there once an ancient civilization of alien life forms? And if so, where did they go? Believe it or not, the idea that Mars was occupied by a race of intelligent extraterrestrials was not the creation of science fiction, but science fact. In the early days of humankind, Mars burned faintly red in the night sky, leading some to equate it with a mighty god, naturally, the god of war. But then astrologers, using a new contraption called the telescope, determined that those lights in the sky might be planets, much like ours. This meant there might be other civilizations, other life forms out there. And Mars was about to become the star attraction. Thanks to Italian astronomer Giovanni Schiaparelli. In 1877, Schiaparelli trained his telescope on the Martian surface and observed the existence of canali. By this, he meant natural channels. But due to an unfortunate translation, these channels became canals, which implied a man-made phenomenon. To fully understand the impact of this, consider that only a few years earlier, human engineers had completed the awe-inspiring Suez Canal. It defied nature and geography by linking the Mediterranean and Red Seas. It was considered the latest wonder of the modern world. Whether or not Schiaparelli believed the canals to be made or natural, the word itself sparked the public imagination. If there were canals on Mars big enough to see from Earth, really intelligent beings must have built them. The rumor was dramatically compounded by an American astronomer named Percival Lowell. Lowell was a highly respected man of good society who had a profound love of astronomy. He developed a fascination with the canals of Mars and sat up through the nights observing the red planet. And what Lowell thought he saw in the wee hours was a dying world crisscrossed by constructed waterways. Perhaps, he wrote, creatures short on water have built an irrigation system that circled the planet. By the turn of the 20th century, the idea that Mars was occupied had hit the mainstream media. New York Times headline, 1911, Martians build 2 immense canals in 2 years. Martian civilization was usually perceived as being ahead of us in evolution. And each earthbound nation projected onto Martian society the diverse vision and fears of its own future. In this 1924 movie from Russia, Mars is portrayed as going through a proletariat revolution and ending up successfully communist. But many thought that Mars was dying, and some said it was only a matter of time before Martians tried to contact us. And so, some thought, they did. through another new technology,
This is Seth Shostak. Go ahead, caller.
radio. Astronomer Seth Shostak takes up the story.
It goes right back to those early radio pioneers, and none so directly as to Nikola Tesla.
One of the most brilliant electrical engineers of all time, Nikola Tesla, was the first to claim someone from beyond this planet was trying to get our attention. In 1899, Tesla was experimenting with an electric invention that essentially acted as a large antenna when he noted something strange. Repetitive signals which were substantially different from the signals he had noted from storms and earth noise.
And it's only natural to imagine that he would ascribe this to some sort of intelligent beings, because as far as Tesla knew, only transmitters could make radio sounds. So he naturally assumed that if he heard something, somebody was broadcasting it.
In fact, Tesla was probably mistaken, as Shostak often gets to explain on his weekly SETI radio show.
Well, we don't know for sure what Tesla heard, but most likely it was something that we call whistlers. These are just distant thunderstorms, lightning discharges that produce natural radio waves that get distorted by the atmosphere as they propagate around the Earth and make a sound that kind of sounds like a whistle.
Modern science may have an explanation, but in a way, Tesla was ahead of his time. The idea that you could send signals from one planet to another made sense and inspired subsequent radio enthusiasts to listen for signals from outer space.
A guy by the name of David Todd realized that in 1924 there was a real opportunity to listen for the Martians. And the reason was that in 1924 you once again had one of those circumstances where Mars and the Earth got close to one another. So he organized an effort to get people to stop transmitting for 5 minutes every couple of hours so that people with the right equipment could actually listen, and this included the military, to listen for signals that might be coming from Mars or some other planet.
But whatever the message might have been, it seems we humans didn't get it. At which point, the Martians turned nasty.
Ladies and gentlemen, we interrupt our program of dance music to bring you a special bulletin from the Intercontinental Radio News.
In 1938, Mars attacked. Turns out it was apocryphal, an imaginative radio play based on the H.G. Wells book, War of the Worlds. But many believed it and thought Earth was under imminent threat from aliens.
Now, mind you, it wasn't so unreasonable. I mean, there were places that really were being invaded at the end of the 1930s, after all. So the mindset of the public was kind of attuned to the idea of hostile forces coming in and taking over.
And sure enough, they came. Martians, great and small, came out of the skies and landed in our movie theaters. Sometimes they looked like giant insects. Mostly they seemed suspiciously human-like, and they came in a bewildering variety of shapes and sizes. They had laser guns, evaporators, death rays, and deadly kisses. They wanted gold, weapons, earth women, and human blood. One thing's for sure, they were very rarely friendly. Next thing you know, real flying saucers were being reported from San Fran to Timbuktu, and the phenomenon of alien abductions was born. The world, it seemed, had gone crazy for extraterrestrials. For all its downside, the popular imagination paved the way for mankind to make that giant leap. In 8 years, the U.S. built a transport system and became a spacefaring people. Perhaps we were determined to bring democracy to the communists on Mars. In fact, we only got as far as the moon. And while there were no aliens up there, you might argue that if we could make the trip, then extraterrestrial life, capable of interplanetary flight, was at least a possibility. So what about Mars? As our technology got better, we sent a robotic scout to the red planet. The landing was a success. The robot touched down, turned on the camera, and we finally got a good look at Mars. It wasn't what we expected.
How disappointing after centuries of assumption that Mars was inhabited, that it had cities, it had canals, and the reality was that it was just this terrible, awful, dead-looking place.
Ladies and gentlemen, we regret to inform you, Mars is dead. Or is it? Mars may be unoccupied now, but if we're to believe Richard Hoagland, the red planet once hosted a magnificent civilization. Hoagland is the principal investigator of the Enterprise mission, a loose collection of scientists, researchers, and Mars enthusiasts. They've spent years trying to prove this extraordinary theory. For Hoagland, it boils down to this.
If I had one catchphrase to describe the whole problem of convincing scientists that there is really an ancient civilization on Mars, it would be, it's the geometry.
Take the face-like structure from this 1976 Viking orbiter image. NASA claims it's a naturally occurring rock formation. Richard Hoagland thinks there's more to it.
If you actually look at proportions, where the mouth is, where the nose is, where the eyes are, they conform to commonly accepted statues and representations of human forms that go back literally thousands of years.
And Hoagland has found what he believes to be a highly complex geometric relationship between various structures centered around the face. Hoagland claims that the layout of this region, named Cydonia, is similar to what we see in ancient ceremonial complexes on Earth.
There are alignments, there's parallelisms, there's right-angle rectilinearity. They also appear to have a specific geometric relationship to the face, to another massive structure down here, to other structures.
To prove his theory, Hoagland and his colleagues have applied a series of computer image analysis programs, looking for, well, basically things that don't match the surrounding landscape. And the face and a couple of other structures register as anomalies, implying, he says, artificial constructions.
This is the real image, and this is the fractal representation. And again, it's the signal strength is basically...
Strictly speaking, a computer will find whatever you program it to look for. It doesn't actually determine whether or not the artifact is natural. But Hoagland claims there are some things you can see for yourself. Take this pyramid, an apparently perfect tetrahedral form with an accurate apex and sharp angles.
This unquestionably had to be made by someone because nature does not produce this kind of structure. If we were to land someday, find the entrances to this thing, walk inside, because if the exterior is preserved in this extraordinarily pristine form, imagine what waits us on the inside.
But if there was a civilization, what happened?
That's where things get interesting, but that's where we obviously cross the line from science to speculation. We have no ground truth, unfortunately.
So why isn't NASA all over this? Hoagland thinks the government is hiding something.
I believe there's a cover-up. Call it a conspiracy if you will, except they're not called conspiracies, they're called policies.
And why? Well, according to Hoagland, it goes back to an obscure Brookings Institution study commissioned by NASA and published in 1960.
There is a section devoted to the implications of NASA's discovery of extraterrestrial life. And the document recommended that if we were to discover, i.e. NASA were to discover evidence of extraterrestrials, that it should be basically kept secret because it had the potential at the limit to destroy civilization.
The argument seems to be that where a civilization comes into contact with one more technologically advanced, that civilization's in trouble. So does this mean the government is covering up aliens to prevent a societal meltdown? It's a bit of a stretch when you consider that all the Brookings report actually suggested was that we should do more studies. Hardly sinister stuff. Seth Shostak thinks there's a fundamental flaw in Hoagland's cover-up theory.
Well, doggone it, if the aliens are really here and they're really advanced and they're really malevolent, as they could conceivably be, then it really doesn't matter what the government does it? This is Bambi meets Godzilla, and Godzilla's gonna win.
This from someone who believes there's life beyond Earth. Shostak works for an organization that operates on the assumption that not only is there life out there, some of it has technology. This is the Allen Telescope Array, built and operated by the University of California at Berkeley and the SETI Institute. SETI stands for the Search for Extraterrestrial Intelligence. It may seem out there, but SETI is an entirely scientific operation, manned by astrophysicists, engineers, and planetary scientists. Their objective is simple.
It's really easy to send signals between the stars. That's the bottom line fact. There might be thousands, millions, or more societies that are sending information from one star system to the other. Why not look for them?
SETI is essentially eavesdropping on the universe in an attempt to pick up a signal from outer space. To do this, SETI uses highly sensitive radio receivers that scan systematically through the billions of star systems in our universe. It's like scanning through your car radio dial as you travel cross-country, but on a cosmic scale.
Now, what kind of signal are we looking for? We don't care. Looking for the message requires a different kind of technology that we haven't built and won't build until we find that they're on the air. We're just looking for a signal that tells us, hey, their transmitter switch is on.
It may seem like looking for a needle in a haystack, but astronomy has made enormous progress in identifying the stars and planets beyond our solar system, which, combined with ever-improving technology, allows SETI to search with more precision. The motive, however, is as old as mankind itself.
We're trying to look for something that would show that, we're part of a bigger picture. We're not just a little bit of chemistry run amok on this small little world tucked away in the corner of a nondescript galaxy in an enormous universe.
So the million-dollar question, of course, has SETI made contact?
In 1997, we picked up a signal using a telescope in West Virginia that looked like the real thing. And we got quite excited to the point where everybody was glued around the computer monitors just looking at what was going on.
The signal had all the qualities SETI looks for in an alien contact. It occurred on a very narrow frequency. This is key because while nature produces radio waves aplenty, they are like broad static across the dial. This one was emanating from a specific location in the cosmos. Throughout the night, scientists were on the edge of their seats trying to pin down the source.
I realized that the world from that day forward will really not be the same. I was very nervous, actually, because I didn't know what the consequences were going to be.
It took 3 days, but the engineers and scientists finally identified the signal, and it wasn't alien.
As it turned out, the signal was due to a European research satellite, the SOHO satellite, the signal of which had just gotten into the structure of our antenna. And that was a bit disappointing.
In conclusion, then, the industry experts, SETI, have not yet found any evidence of extraterrestrial intelligence.
As of now, one thing you can say, and that is we have not conclusively proven the existence of any life, intelligent or not intelligent, beyond the bounds of Earth.
And what about Mars? Martian monuments aside, you'd be forgiven for thinking that 30 years of remote observation has done nothing but confirm our nearest neighbor is dead. But in fact, life on Mars has begun to make a comeback. It's all about water. When NASA scientist Chris McKay saw those 1976 Viking images of a dry, barren Mars, he was intrigued.
I remember the overwhelming impression I got was the lights are on, but nobody's home.
What McKay is referring to is what he poetically calls the ghost of water past. He's offered to meet us in the Mojave Desert to explain.
There's no water in this lake bed now, but the geology, the surface of the ground, shows evidence that there was water here. And that's what we see on Mars. We see dry lake beds. We see river beds that have no water in them, but clearly did at one time. And this is the evidence that Mars had water. And it's that water that's of interest to us from a biological point of view.
Although, in fact, the Mojave gets a whopping 5 inches of rainfall every year, Dr. McKay uses this desert as a near waterless zone to conduct experiments relevant to his theory about Mars. And life, it seems, can thrive nicely in these conditions.
We find microscopic life, microscopic algae, that have learned to survive under dry conditions. This organism, this algae, is the dry version of pond scum. They wait out in the dry for months, maybe years, and then a rain comes and they very quickly set up shop and do their biological thing, and then it gets dry and they shut down and wait again.
Dr. McKay certainly isn't claiming that Mars is populated by desert algae, but he thinks the odds are in favor of past life.
If we were to imagine what would the last Martian have been like as Mars went from a fairly wet, Earth-like environment to the dry desert that it is today, it would have been probably an organism like this.
Microbes? So much for the Martian monsters of the silver screen. But microbes bring us full circle. The fact is, some scientists believe we've already found life on Mars. And it's all because of mysterious clues in a Martian meteorite. Turns out our favorite Martian may be more like our favorite microbe. The 1976 Viking mission to Mars was a triumph of modern space exploration. But one unexpected bonus was information that could be used to further study our alien visitors. The unidentified meteorites sitting in cold storage on Earth.
Well, we've had meteorites we've known were meteorites for 100 years, but we didn't know they came from Mars until Viking landed and measured the gases in the atmosphere, and scientists studied the gases in these meteorites and showed that they were the same.
But how does a Martian rock get to Earth? Scientists think that some explosion, probably caused by the impact of an asteroid hitting Mars, blasts a rock off the planet and into space. It then hurtles around our solar system until, if it's very lucky, it gets caught by the gravity of our blue-green planet and plunges to Earth. Imagine the odds. For NASA scientist Dr. Everett Gibson, this event began a remarkable voyage of discovery.
For one to have life, you have to have the presence of water, you have to have the presence of carbon, you have to have an energy source, and you have to have geological processes. All of these four fundamental things are seen within the Martian meteorites. So, the conditions could be right for life to exist on Mars, perhaps in the past.
And it seemed the NASA team was about to prove it. Thanks to that odd little meteorite, 84001, from Mars.
600 million years after this rock was formed in the crust of Mars, you get water percolating through the rocks, saturated in carbon dioxide from the Martian atmosphere. As the water basically evaporates away, it potentially leaves the carbonate behind.
So the meteorite confirmed that Mars had once been wet. But there's more.
The carbonates contain organic matter. The carbonates contained an iron oxide mineral, magnetite.
Here on Earth, magnetite, essentially magnetic crystals, are often produced by microscopic life forms. This was getting exciting. Using the most powerful microscope at their disposal, the investigators now looked even closer and got the surprise of their careers. They saw what looked like minute, worm-shaped structures. Quietly elated, the scientists were cautious.
We said one explanation could have been biology operating. Could have been the signatures of something like a life process.
So was this finally confirmation of life on Mars? Well, from the moment they were announced, the microbes have been controversial. Critics say that the carbonates, organic matter, and magnetite crystals can be explained through other non-life processes, and many believe that the worm-like structures are actually clumps of a coating material used to examine the sample in the laboratory. Still, others point out that the rock could have been contaminated at any time, perhaps when it was lying around for thousands of years here on Earth. Nevertheless, the possibility of ancient Martian bacteria raised the ante on life on Mars. If once upon a time Mars was warmer and wetter and had some early form of microbial life, did it survive, thrive, and grow up to build like an Egyptian? Well, it's a nice idea, but seems unlikely when you consider that conditions on Mars are dry, radioactive, and extremely cold. How could anything survive in this hostile environment? But we could be underestimating the nature of life itself. Microbial life, that is. Believe it or not, astrobiologist Penny Boston is searching for life on Mars by dropping deep into this heart of darkness. This is a lava tube, a subterranean cave formed by underground lava flows during volcanic eruptions that occurred thousands of years ago. And Boston has someone she wants us to meet.
Sometimes they're in crevices. Sometimes they're kind of hard to see.
Is this when the scary monster reveals itself?
Ah, there's one.
Actually, no. This is an extremophile.
We're looking for what we astrobiologists call extremophiles in this environment, and that means that they're organisms that are living in very difficult conditions. In this particular case, these organisms are living in a very cold cave right around freezing. They are making their living without benefit of sunlight, and there's almost nothing to eat in this cave.
In recent years, scientists have discovered tenacious microorganisms living in all forms of extreme environments. So if on Earth, why not on Mars?
We think that Mars is covered with lava tubes. We believe that by looking at organisms that live in these extreme circumstances on Earth, we can learn a lot about what to look for on Mars, and that similar Martian organisms may be able to persist on Mars in places very similar to this lava tube.
To find out, Dr. Boston has created her own little Mars environment biospheres, essentially exposing a range of microscopic Earth life forms to various elements to be expected on Mars.
They have been subjected to Mars-like levels of high ultraviolet radiation and Mars-like temperature cycles. We have given them atmospheric compositions from very low levels of carbon dioxide with nothing else to perhaps 1/10 the density of Earth's atmosphere, and tested them under those conditions.
And so far, she's isolated 36 different strains of organism that thrive quite happily. So in theory at least, life could survive the harsh conditions of Mars, except for one problem.
There's one thing for sure that we know, and that is that all forms of life on our planet require liquid water. We don't know if that's going to be true on other planets, but we think that where there's going to be life, there's going to have to be water.
This simple fact has helped scientists in the 21st century refine the search for life on Mars into a comprehensive strategy. Dr. Jim Garvin is chief scientist at Goddard Space Center and a veteran of NASA's Mars exploration program.
NASA uses a term, follow the water. Following the history and record and abundance and inventory of water is a wonderful way to search for something as tough, perhaps elusive, as life.
We already know that Mars was wet in its ancient past and has reservoirs of ice in the polar caps. But using remote sensing technology, NASA has found what could be evidence of a modern water cycle.
We've discovered tens of thousands of hillside gullies that clearly released a fluid, likely liquid water, in the extremely recent geological past.
They've also discovered that Mars has a vast underground reservoir of ice, spanning about 30% of the planet.
The reservoir of water under the surface may include liquid zones. They may be liquid under the ice caps, they may be liquid hundreds of meters deep, they may be liquid tens of meters deep. All that points to a modern liquid water cycle on Mars.
Where there's water, there could be life. And when it comes to the question of life, Dr. Garvin is a believer.
Absence of life in all senses of the word throughout time on Mars. Is that a possibility? I actually believe not. All the right building blocks, initial conditions, the same that we think persisted in early Earth, must have been at Mars. So, the tale of two planets. Where do they diverge?
It is this that drives the international space community to take aim at Mars. Over the past 30 years, dozens of unmanned missions have been launched. But the Red Planet has become something of a Bermuda Triangle, with roughly 2/3 of all missions ending in failure. Given the danger and high ticket price, plans for a manned mission have been delayed for decades. For Dr. Bob Zubrin, it's a dream that he refuses to let go.
NASA had plans to send people to Mars by 1981. Those plans were credible. We should have been on Mars a quarter century ago.
Bob Zubrin is president of the Mars Society, a coalition of scientists from all walks of the international space community. The Society has been lobbying Congress, NASA, and the government for years, determined to keep Mars exploration on the radar screen. And Zubrin has been practicing. the Mars Society has set up Mars analog habitation modules in the deserts of Utah and the remote landscape of Devon Island in Canada.
What we're doing at these stations are really what someone would call operations research. We're trying to find out what field tactics and techniques would be most usefully applied on Mars, what technologies would be most useful to the crew.
And Zubrin has more in mind than a quick trip across space. He plans to colonize the planet.
We're going to Mars because Mars is the planet that has on it the resources needed to support life, and therefore potentially someday human civilization.
For Zubrin, Mars is the new frontier.
Whether or not there has been life on Mars, whether or not there is life on Mars, there will be life on Mars. And it will be us.
Zubrin isn't the only one with plans for the Red Planet. Dr. Chris McKay champions another idea, essentially to kickstart the biosphere.
If we go to Mars and find that there is no life, then I say we might as well move in.
And in the case of Mars, that begins with warming up the planet.
Well, we know how to warm up planets. We're doing it on Earth.
By introducing preferably non-harmful greenhouse gases into the Martian atmosphere, we could start a chain reaction.
The effect of these gases would be to melt the ice, bring back the atmosphere, and restore Mars to the conditions it was billions of years ago.
Right, but if we're going to live there, we're going to need oxygen. Well, Chris McKay has that covered.
These organisms are known as cyanobacteria. It's a type of algae, a single-cell type of algae, that has a very long history on Earth. These were the organisms that first made the oxygen. And these organisms could do the same thing on Mars. Send them to Mars and ask them to change the world.
Cyanobacteria, the planet changers.
These are the little green men. They're not men, but they are little and they are green.
But wait, what about the pyramids? The supposed signatures of an ancient Martian civilization. What if the guys that built the face are coming back? Mars. Could that enigmatic face in the hills of Cydonia really be a calling card from a lost civilization? Ironically enough, we might pick up a clue at the World Science Fiction Convention in Southern California. No, we're not looking for Martian monument builders. We're here to meet astronomer Phil Plait, a scientist on a mission to provide participants with a healthy dose of science fact. Today, he's taking on the face on Mars.
Just so we're clear on this, it's a rock that looks like a face. And it's not even that good of a face. It looks like he's got, I don't know, Isaac Asimov.
Phil Plait is the creator of Bad Astronomy, a website and book dedicated to debunking what he calls pseudoscience. For him, the solution to this Martian riddle is elementary.
There's a trait called pareidolia. And it is the tendency to see faces in random patterns. And we see this all the time. You can find lots of features on Earth. I once saw Lenin in my shower curtain. It was just a water stain in my shower curtain. But man, did it look like Lenin.
Why do humans do this? One possible explanation for seeing faces in random patterns is that it's a survival technique going back to infancy. Unresponsive babies are more likely to be ignored or abandoned. So to make sure he gets mom's attention, a baby will seek out the image of a human face and gurgle adorably. Whatever the reason, Phil Plait thinks we can't always trust the evidence of our own eyes.
Our brains don't like random patterns. They want to find some sort of real pattern in the noise, in the randomness, even if it's not there. And so you can just take a collection of dots and you might see a head, or you might see Jesus in it. But that's just your brain trying to find a pattern desperately in something that is patternless.
If you take a closer look at the Martian terrain, the planet explodes with faces. Face-like patterns, Plait insists, not monuments to ancient civilizations. Richard Hoagland, the leading advocate for the theory of monuments on Mars, has countered this argument for years. He insists his theory is based on more than just a pretty face.
If I had to stake my entire almost 30 years now looking at this, that there was at one time intelligent life on Mars and they built something, I would say the geometry of Cydonia is now trillions to one against it being chance, and in any any man's or woman's science, when you have that level of odds in your favor, you can say with relatively good backing that it's real.
Fair enough. Let's ask the scientist. NASA scientist Jim Garvin has this to say about geometry.
It is possible to construct geometric patterns between anything. There's an infinite number, in fact, of different affine geometric patterns between this feature and that feature and this feature and that feature. To read one as being the answer to this particular small patch of Mars is extremely challenging to me and to the science community.
But what about those interesting pyramids and tetrahedral-shaped landforms? Just the wind, says Garvin.
If the wind is blowing one way for a while, and the next season it blows this way, and the next season it blows this way, and the next season it blows this way, what happens? Over time, if that's the consistent pattern of the wind, sandblasting, in this case a hill about 10 blocks in scale, you can produce landforms that remind one of pyramids.
Similarly formed natural structures called yardangs are found in the dunes of Egypt's western desert. In short, Dr. Garvin sees the Cydonia region as a natural landscape shaped by the forces of erosion. So what about the face?
When I look at this picture on Mars, I see positive relief landform, a hill of the scale of multiple city blocks, very similar to tens of thousands of others on Mars.
But Dr. Garvin insists you can't prove anything with a two-dimensional snapshot. In order to analyze the structure, he's created a 3D model of the landform by combining topographical data with a high-resolution 2D image. Now he is able to observe the face as if he were flying around it in a helicopter. And from this height, the Sphinx dissolves into landscape. No eyes, no mouth. Remarkable only because this is a hill on another planet.
There's a lot of different interesting ways to look at this feature. The simplest way is the natural way. And that's always worked well in science.
Just one more thing. Why doesn't NASA send one of its robots to take a look? Well, considering the enormous cost and the physical challenges of dropping a priceless asset such as a Mars rover, the target must surely be chosen with careful consideration on the basis of scientific priorities.
Why would we consider this a first priority? And that's the question I leave you with. We're looking for our origins in the history of life in the universe. And there is no evidence that that has a bearing on that question today.
In the end, it's up to you to believe in the magic of ancient monuments or the world of modern science. So Mars. For centuries, the red planet has kept us guessing. First, it was home to an advanced civilization and the Martian invaders of our silver screen. Then, it was a cold, dry, barren planet. And now, it offers the possibility of life, with mysterious clues in a Martian meteorite and the suggestion of water once thought long gone. But is there life on Mars?
I think odds are we won't find life. There's no evidence, so I'm not going to bet my house either way.
But the desire to know drives us ever closer to an answer that may also hold the key to our very place in the universe.
We live in space as small, minuscule amounts of the matter that is the bigger space. The more we understand the history of life in this solar system, in this universe, the more we understand our own life and our own destiny.
It's been 30 years since a human last set foot on another world. If space exploration is to become a reality, not of the past, but our future, perhaps it's time to set our sights on Mars.
There's some moments in history where you have the capability of doing something important, and I think that this generation has the capability of finding out whether we're alone or not.
Either way, it's something we need to know.
If we search the universe and we find no evidence of life, we should start taking seriously the possibility that life on Earth is unique, really unique, and that in a very real way, the contribution of Earth to the rest of the galaxy, to the rest of the universe, may be life itself.
Alone in the vastness of space, perhaps even the worst of our Martian nightmares is better than galactic solitude. one thing is certain. Our best hope for finding out if life exists in the universe lies on our sister planet, the Red Planet, the remarkable neighbor we call Mars.
There's a battle going on out there that will determine the fate of the universe. It's a battle between two great forces, one trying to pull the universe together and the other trying to push it apart. We travel to when time began to find the universe in a beach ball.
Thanks for passing me the universe.
We go down a mine to look for what's pulling the universe together.
If you're an astronomer and someone says you don't know what 2/3 of the universe is made from, that irritates you.
And we look for what's pushing it apart by searching for exploding stars. Hope I find one. I'm Alan Alda. Join me as Scientific American Frontiers ventures out into the dark side of the universe.
This program was made possible by the National Science Foundation, America's investment in the future. And by contributions to your PBS station from viewers like you. Thank you.
Once we thought our world was the center of the universe. And today we know we're on a minor, if privileged planet, circling an average star in an inconspicuous spot in an unremarkable galaxy that's just one of billions of galaxies, occupying a universe that stretches farther than we can see, even with our biggest telescopes. But in the last few years, telescopes like these here in Chile have shown us that we're even less at the center of our universe than we could have ever imagined. You and I and these rocks and the sun that shines on us and the stars that twinkle overhead aren't even built of the same stuff that most of the universe is made of. And there's a mysterious force out there in space that literally comes out of nowhere. It's a force that seems to be pushing the universe apart faster and faster, until one day everything out there beyond our own little solar system will simply disappear into blackness. Our universe and our place in it just got a whole lot weirder. Staring at a patch of sky 1/10 the diameter of the moon, the Hubble Space Telescope recently peered farther out into our universe and farther back in time than any telescope before. For 1 million seconds it gazed, gathering light from 10,000 galaxies. The smallest and faintest are some 13 billion light years away, meaning their light has been traveling toward us since shortly after the universe began. What gave birth to these first galaxies is one of the great mysteries of our cosmos. But astronomers now suspect that matter we can see in the universe, including ourselves, resulted from a titanic struggle between a form of matter we can't see, dark matter, and a force, dark energy, that we've only recently detected. Together, dark matter and dark energy rule our universe. And we're here to wonder about them only because in their battle for domination, which has gone on for most of eternity, neither has triumphed.
2, 1, main engine start, and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
This was the launch on June 30th, 2001, of a spacecraft able to look even farther back in time than the Hubble. Called WMAP, its mission was to capture the very first light of the universe. That light has been traveling toward our own little corner of the cosmos ever since it was released from what most astronomers now agree was the origin of everything we can see. Planets, stars, galaxies like our own Milky Way, and the billions of other galaxies that have been expanding outward since the beginning. That beginning was the Big Bang, a ripping open of space and time, inflating in an instant to become an unimaginably hot cauldron of energy and matter. It was light escaping from that cauldron that WMAP was sent to measure. Light now reduced by its journey through eternity to a faint afterglow called the cosmic microwave background radiation. What the satellite saw has been mapped onto something I can comfortably get my hands around, if not yet quite my head. This device, this satellite, is picking up this cosmic background microwave radiation from way back in time.
Right.
From the beginning of the universe.
It's actually a direct picture of what the universe used to be like because it took that light all that time to get from there to the satellite.
Okay, here's the you have to help me visualize this.
Okay.
A lot of us, when we first hear about the Big Bang, think of it like an explosion happening in a point in space and moving out. And then somewhere we're in that or something. And a lot of us think when we look back in time, we want to look back to that point. But on the contrary, when you look back in time, you're looking in every direction. You're looking all over some shell.
Exactly.
And everywhere you look, it's as far back as you can go. How could that be? Can you explain that? Can you give me an image that helps me grasp that?
You're trying to think of an explosion that happened in one place.
Yeah.
And instead, the universe was... Today, it doesn't have any particular center, and it never did. Everywhere you would have gone, it would have been expanding.
Yeah.
I like to think of baking a loaf with little raisins in it, and when the bread rises, all the raisins are moving away from all the other raisins. No raisin can really claim that it's in the center of this expansion any more than any other, right? And this is the same way we need to think of our space.
I know, but here's the problem. Every time one of those raisins wants to look at another raisin,
it
can look all the way across the loaf to a raisin on the other side, but if it looks in the other direction, it sees the baking tin. That's a little bit different.
That's because the bread is finite, and we live maybe in an infinite space. If you live in an infinite loaf of bread, there's nothing you can do to tell the difference.
The picture of an explosion and a ball of stuff is, I agree that that's what many people think of, but that's just wrong. It's not what the Big Bang Theory is all about. What the Big Bang Theory is all about is space itself. Think of it as being stretchy, and it's just constantly stretching, and it's stretching between every object everywhere, so that everything is getting farther away from everything else. And no matter where you are and you look out, you see a glow left from the
So it needs to be called the Big Taffy Pull.
Well, that would be a better name. Almost anything would be a better name.
The infinite, then.
The infinite taffy pull.
Yes.
Okay. Well, I think you're getting me closer. All right. Okay. Show me what the implications of this mapping are.
So what I really love about Chuck's beach ball is that it represents this very basic fact that even though space itself may be infinite, we can only see a finite volume. It's a huge volume. This is about 13 billion light years in radius, but it's still only finite, right? So we're in the center of this, and the most distant thing we can see is this hot glowing wall of hydrogen plasma, which is opaque. So, we just can't see what's on the other side.
But on the side of the wall we can see, on our beach ball, it's the inner surface. The incandescent plasma just beyond has cooled enough to go from being uniform and featureless to having eddies and ripples. It was these tiny imperfections that were imaged by the exquisitely sensitive eyes of the WMAP satellite.
Chuck and his colleagues have stretched the contrast here by a factor of 100,000 to prevent it from looking completely uniform. But there are, nonetheless, these tiny ripples where some places look hotter, others look colder. And that's just because there was a tiny bit more stuff in some directions than in other directions. And these little ripples are extremely important because it's because of them that we're here. If you just had something which was always uniform, it would stay uniform forever, and you would never make clumps, planets, and we couldn't be here talking.
To find out more about how those faint early ripples left over from the Big Bang became our universe, we've come here to the foothills of the Andes in Chile. This region has become home to some of the world's biggest and most powerful telescopes. Lured here by clear skies and a smooth flow of air off the Pacific Ocean that reduces atmospheric turbulence, making for what astronomers call superb seeing. This is the site of one such observatory, Las Campanas, run by the Carnegie Institution of Washington. and the principal research site of an old friend of Frontier's, Alan Dressler.
Well, welcome to the Western Planets Observatory, Magellan telescopes.
Thank you. There seem to be two.
There are two. They're twin 6.5-meter telescopes, which means they have mirrors that are about 22 feet across, which is a good size, and they collect light from distant stars and galaxies. And this is where we do most of our research. Hi, Miguel.
Hey, how are you?
That research is focused on the formative years of the universe.
At the beginning, we know there was a very simple distribution of matter. It was very smooth. It was very simple elements, hydrogen and helium. There were no stars, just gas. How did the universe go from being deadly dull with no variation to tremendously complex so that there are creatures on it that look back and figure it all out? That's the fundamental question. And this zone, this sort of 3 billion years in to maybe 8, is where most of that complexity grew. And we can see that evolving, happening by this strange ability to look back in time. I mean, only in astronomy can you actually look back and see 5 billion years, 10 billion years into the past. You can see the past because it took the light.
All those stories about time machines.
Yeah, it is.
We got one. We're looking at. The light from the stars comes in and hits that mirror.
Exactly. Gets reflected on another mirror that's above
that
us
little guy
here.
up there.
The little guy up there, which in turn reflects then the light through the hole in the black turret where there is another mirror, a diagonal mirror, 45 degrees, which directs the light to the instrument.
When the light hits that mirror, how long has it been traveling?
Well, for the things that I'm looking at with Pat tonight, the light has been traveling for about 10 billion years. So pretty much the whole age of the universe. And this is the first thing it hits after all that time. So it's got to be cleaned.
Especially tonight, because it's the first time Alan will be using a brand new instrument.
Alan, this is Pat McCarthy, my science partner here. This is the slit mask.
So if you turn around and look through the light, you'll see.
In what they affectionately call the wok, Pat has painstakingly cut tiny holes corresponding to the galaxies he and Alan plan to study.
In any area of the sky that we pick up, say 1/2 degree across, that's what this is looking at, that's the size of the moon, there will really be 100,000 galaxies, very faint, very distant galaxies. And we have selected, in this case, 700 of them we want to look at. So we must make sure that the light from those 700 goes through the spectrograph, but nothing else.
Alan's new instrument doesn't just take pictures of those distant galaxies, it can read their spectra. In fact, nearly everything we know about stars and galaxies comes from analyzing their light with the aid of a prism, or more commonly, a device called a diffraction grating.
When sunlight or any light strikes this, it's spread by color into its component colors. You can say how much red light, how much green light, how much blue light tells you something about the temperature of the sun. And the sun is a star at 5,000 degrees temperature, produces a lot of yellow light. And so the middle of this spectrum and the most intense part is yellow-green.
And then we can see almost with our bare eyes. We see red stars and bluer kind of stars. That has to do with the temperature of the star, basically.
Here, for example, in one of the first images taken with Alan Dressler's new camera, both red stars and blue stars are visible in a galaxy nearby. But in the spectrographs that astronomers use, the colors of a star can be analyzed in much finer detail than is visible in a rainbow. There are lines at precise locations across the spectrum that reveal what a star is made of, as well as its temperature and its size.
The reason that's important is different stars of different size last, they live a different amount of time. The sun will last for 10 billion years. It's halfway through its lifetime. A star much more massive than the sun might only live for 1 billion years. So if we find those, we know that those are young stars. They cannot be any older than 1 billion years old because they would already be gone. So when I look across our galaxy, I could do them one by one. I could tell you what each individual star is like. I could see a star like the sun all the way across our galaxy. And if I put together the light from billions of stars, I could see them all the way across the universe. And in that information is the rate at which new stars are being born in that galaxy. 3 billion years ago, 5 billion years ago, 7 billion years ago. So I begin to build up a picture of how rapidly were galaxies turning their gas into stars over their lifetimes. A complete construction project.
At twilight, the Magellan Telescope's dome is opened.
We need to rotate 0.335 degrees. Plus 0.335. Trace, 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 cinco.
So how many galaxies are going to have their spectra taken?
We're going to take spectra of 700 galaxies tonight.
700?
Yeah, that's probably as many as ever been done. You got to remember to put in the walk, because that's a big mistake. If you don't do that, you really blown it.
This first exposure using the wok took a half an hour.
Okay, so already we can see some objects. That's encouraging. There's a bright one.
This is just the beginning of several months' work that will add up to some 50 to 100 hours of data. But even from these first few minutes of peering across the universe, a trickle of light has left the signature of a galaxy in the full fury of creation.
So here is a very faint line that is a very faint galaxy, very far away. And here at this one color, that represents probably 100 photons of light coming from a place where 1 million hot young stars have formed in that galaxy 10 billion years ago.
So it's 10 billion years ago, and all that made it to us tonight were 100 photons.
That's right.
So this is the first scientific run you've done, huh?
Yes. New instrument.
How do you feel? Is it a good start?
It's a good start. I wish we had seen a lot in the first exposure, but you have to have a lot of patience if you're going to do something really hard. But it works. The instrument works. It's producing spectra.
You've been working on this instrument for how long now?
6 years.
6 years.
It took a long time to build, but now it's going to pay off for us.
That payoff will help illuminate one of the universe's darkest secrets. How those early ripples left from the Big Bang became the seeds of the stars. A vital clue to that mystery was discovered because a little girl loved watching the movement of the stars in the night sky outside her bedroom window. That story next. In the early 1970s, Vera Rubin was a rare young woman in the traditionally male-dominated world of astronomy.
I got interested in astronomy by watching the stars as they moved outside my window. I had a window that faced north. I had a bed under the window, and I could see during the night that the stars changed their positions, and that's really what got me interested in astronomy. So I guess I was always interested in how things moved.
Vera decided to look at how stars move in spiral galaxies, like our own Milky Way, as they revolve majestically in space. Most astronomers then studying galaxies were drawn to their centers, where the stars are densest. But as a then shy young graduate student, Vera looked instead to where galaxies trail off into empty space.
I had children, and I didn't want to compete with what other people were doing, so I decided to study the outsides of galaxies.
What she discovered there was revolutionary in both senses. In our solar system, the planets revolve more slowly the farther they are from the gravitational attraction of the sun. Galaxies were assumed to rotate similarly, with stars moving more slowly the farther they are from the center. Instead,
I found that the stars very far out were going just as fast as those near the center, sometimes even faster.
Sometimes faster.
Sometimes faster, and well beyond where there was no light. In fact, I went to my office this morning and got this. Here's Andromeda, which is the largest galaxy, largest spiral near us. At our position in our galaxy, which would be like maybe a third of the way out here, we're moving at 500,000 miles an hour around the center of our galaxy.
You hardly feel a wind.
That's right. And you don't notice it because everything around us, all the stars near us, everything is going just at the same speed that we are.
Yeah.
So here are the velocities of stars and gas all the way across. Newton's laws, because this is where the luminosity is, would predict that the velocities rise and then fall rapidly, so that by the time you get out to what looks like the edge of the galaxy, the stars would be moving almost negligibly, very, very slowly. So what you see instead is they're moving very, very fast, all the way out there.
So when you got that information, then what did you think you were wrong, or did you?
No.
You knew you were right.
I never thought I was.
Everybody never thought you were wrong.
I never thought. No, I had some crazy ideas, and then it shortly settled that what would have to be was matter that isn't luminous, that you don't see. The galaxy has to extend that far out. There has to be something. There has to be matter that's gravitationally accelerating the little bit of gas that we could see.
The bigger the wobble of the star, the more it's doing that, the bigger the planet is going around it, and the faster it wobbles, the closer it is.
That's exactly right. Yeah.
Okay. So in that way, you can really tell us what's there.
That's right.
Deborah and her colleagues have found some 70 of the over 100 planets so far discovered orbiting other suns. Most of these planets are huge and orbiting fast, making their detection easier. Deborah's team's most dramatic discovery attracted the attention of a 4th grade class in Moscow, Idaho.
And when we found this system, this first star with 3 planets, they sent me a letter, Dear Dr. Fisher, we've been reading about this discovery in the newspaper, and we're doing, scale models of the solar system with paper plates, but we wondered, if you'd named the planets yet, because if you haven't, we have a suggestion. And so they said the planet that's 4 times the mass of Jupiter should be called Forpiter. and the one that's 2 times the mass of Jupiter should be called Tupiter, of course. And then the little one that just orbits every 4 days should be Dinky. So.
The star that Deborah's observing tonight, she's already looked at some 200 times. And while it used to be thought an unlikely candidate to have a planet, she's now picking up the faint trace of a wobble. Planets are thought to form from disks of dust and gas that surround a sun. And it could be that many of the billions of stars out there have planets so far undetected. The fact that you're looking for planets that so far haven't been seen, mostly, is that some of the missing matter, or what?
That's a good question, and that's one of the early hypotheses, was that maybe the dark matter is just planets. After all, we now believe that planets, when they form, some of the planets fall inward, but others are ejected from their solar systems. And the best way to get a handle, sort of a back-of-the-envelope calculation, is to look at stars that are forming, being born out of molecular clouds, and to imagine that all of the material in these typical disks around the stars is ejected. Let's just take that as an approximation. And then, would that be enough to make up all of the missing mass? And the answer is no, that the calculation has been done, and that it probably isn't, it's orders of magnitude too low to account for the missing matter.
In fact, not only is most of the missing matter in the universe probably not the stuff that stars and planets are made of, it's probably not the stuff that anything is made of. Here on the Yorkshire coast of northern England, the search for dark matter has gone underground. This is the Boulby Mine, whose mile-deep shafts provide cover from something tantalizingly similar to the prime suspect for missing matter.
And if you're standing on the surface of the Earth and you put your hand out, you get hit. 1 cosmic ray a second goes through your hand. And that would spoil the detector signal that we're looking for. So we go deep underground, and then the large amount of rock between us and the surface shields us from the cosmic rays. So when we're down in our labs, rather than 1 a second going through your hand, it's 1 a week.
But while cosmic rays are exotic, at least they're made from subatomic particles that science is familiar with. By contrast, the things Nigel Smith is trying to detect are bizarre even to physicists. Here, a mile down in a vein of rock salt mined to spread on the winter roads of northern England. He's in a race with some half-dozen groups set up in similar underground labs around the world to be the first to detect what are called, with tongue-in-cheek, WIMPs, for weakly interacting massive particles. WIMPs have the apparently paradoxical property of being massive in the sense that they exert a gravitational tug, while being almost completely unable to connect with ordinary matter in any other way. In fact, to call them weakly interacting is to be generous.
Most of them pass straight through the Earth and don't even notice. Most of them pass straight through the Sun and don't even notice. But every so often there's just one or two a month or a year will actually hit a nucleus head on. And that nucleus recoils, and it's that recoil that we're looking for. But the majority of the billions of WIMPs that are passing through as we stand here every second, they just stream straight through, and you never see them.
This is just one of 3 different kinds of detectors here at the United Kingdom's dark matter hunt. And the research project has just constructed a large new underground facility to house them. There are other detectors in tunnels beneath the Apennine Mountains in Italy, where a joint Italian-Chinese team has been claiming evidence for WIMPs, a claim met with skepticism from their competitors. While in the United States, a new facility is being constructed in a mine in northern Minnesota. All this effort to detect a hefty ghost particle that may not even exist. For those involved in the hunt, there's no doubt that it's worth it.
It's a fantastic question. If you're an astronomer and someone says you don't know what 2/3 of the universe is made from, that irritates you, right? So you want to go out there, you want to find out what it is.
And astronomers aren't the only ones in the hunt, which is why I find myself driving a golf cart through the longest building in the world, the Stanford Linear Accelerator in California. I'm following the track of a subatomic particle as it's accelerated during its 2-mile trip to a speed approaching the speed of light. Eventually, the beam of particles will be divided and spun around a couple of loops before crashing head-on into particles coming in the opposite direction and smashing into smithereens. We're visiting the collision point, appropriately, with both a particle physicist and an astronomer.
The beam of particles will come down here and go through that pipe.
And then you hope that an electron and a positron will meet, annihilate, and new particles will be born.
It's from collisions like this that scientists have built up their picture of the fundamental particles of matter in what they like to call the Standard Model. But for the Standard Model to work, physicists have been forced to invent a strange mirror world in which the known particles have ghostly cousins called supersymmetric particles.
This extra set of particles we haven't discovered yet, but they're our best candidate. We think it's the smoking gun for the dark matter out there. So you and I aren't made of these supersymmetric particles, but the dark matter that's controlling a lot of what's happening in our universe is made of these supersymmetric particles.
That's the best theory.
That's our best guess at this point.
Now, this is interesting. You are pretty sure, or are you dead certain, that these supersymmetric particles exist or have existed?
We're going to get different answers.
Less than pretty sure, but if this were a horse race, this is the one I'd be putting my money on.
It is thought that supersymmetric particles are all over the universe?
They're out there.
Yeah.
Yes.
And how did they get started? Where do they come from?
On the Big Bang itself.
From the Big Bang. So are you trying to create a situation something like the Big Bang, where you get both the particles and the supersymmetric particles, the mirror versions of them? But I thought you needed something I thought you needed a lot more energy than you could possibly get on Earth to create a Big Bang.
We're not recreating the Big Bang.
Right, thank God, because I would stand a lot further away from it, and I'd wear that hat.
But we are able, if we have enough energy in our particle accelerators, to create the constituents that were created in the Big Bang.
And so, at the same time that astronomers are going underground in their hunt for the missing dark matter, particle physicists too are burrowing to build the biggest atom smasher ever in the hope of creating dark matter. This is the construction of what's called the Large Hadron Collider at CERN in Switzerland. Due to come online in 2007, the LHC will have gigantic detectors designed to peer into the wreckage of particle collisions of truly stupendous energies. If not quite the Big Bang, then certainly the closest we've ever been to it. The closest we've actually been to it, of course, was with the WMAP spacecraft, which mapped the ripples left as the Big Bang cooled. In the pattern of these ripples, the WMAP scientists see direct evidence for dark matter.
You only get this if you have about 6 times more dark matter than all atoms combined.
What we did is we generated literally tens of millions of possible universes on the computer, and we compared them with our measurement of the real universe that we have. And I think of it as like matching fingerprints. So this is the actual fingerprint of the real suspect, and we have a mug book of fingerprints, and we match them up, and we pick out the right suspect that way. And as Max described, that the right suspect has this substantial amount of dark matter in it.
Today, then, the evidence is mounting that most of the stuff in the universe is not only invisible to us, but isn't even what the visible stuff is made of. But to astronomers like Alan Dressler, looking back in time to see how the universe began, dark matter is more than just astonishing. It allowed us to be.
You're taking this picture of way back in time, and you're seeing the formation of the stars. And what role does dark matter play in that?
It's very important to see how galaxies form, but they couldn't have formed, we now believe, without the dark matter, because there wasn't enough gravity and all this kind of material that we're made of to coalesce and make stars. And that's where the dark matter played the pivotal role. It actually held this, what we call baryonic normal matter, together and allowed it to begin to concentrate and to cool and then make stars. So that transition from, already there were these sort of wells, these places where gravity was strong, and all those atoms suddenly said, oh, there's gravity here from this dark matter, and they headed in that direction. So they fell into those little wells of gravity that had been growing since the Big Bang.
But if dark matter's gravitational hug was indispensable to our universe's birth, we now know that from the start, it's been opposed by an anti-gravity force that might, if things had turned out just a little bit differently, have overwhelmed it, and instead blown the infant universe apart. That story next. In the early 1990s, 2 groups of astronomers came up with a new idea for discovering the ultimate fate of the universe. Both groups, which were soon to become rivals, used several telescopes in their quest, including this one at Cerro Tololo in Chile.
They've had their nights on the telescope, sometimes actually immediately after our nights, or in between our nights.
So do you go around looking for scraps of paper the other one's left, or what?
No, sometimes we look at, we try to figure out what they've observed, but usually it's a friendly rivalry.
Both teams used the telescope to look for the same thing, the death of a star. But not just any stellar death. A particular kind caused when a companion star dumps material onto a so-called white dwarf until the white dwarf reaches a critical mass and explodes. This is called a Type 1a supernova. And the astronomers like it because all Type 1a supernovae are almost exactly alike. Identical flashbulbs popping off randomly all over the sky.
With just a 2-minute exposure on this telescope, we can see halfway across the universe. Nice. That's how powerful the telescopes are and how bright supernovae are. So we can take very short exposures and cover large parts of the sky to discover supernovae.
But discovering them is only the beginning. Once a supernova is spotted, Other, even bigger telescopes are standing by to pounce on its light and read its spectrum.
If we don't find supernovae in this telescope, then all the other telescopes are waiting, have nothing to do.
Right.
They get real mad at us.
Is this the first time you're observing in this test?
Yeah, this is the beginning of our season. So we're going to go 3 months now, 30 half nights searching for supernovae, and tonight is the first night.
So your exposure is covering all of this, and that's even more than a full moon would be in the sky. So what's the probability that you'll find a supernova?
In this one field?
Yeah.
It's about 1.
It's one for this month.
Yes.
But so sometime during this month, you're going to, if you keep pointing there, you're going to catch at least one. Right?
Oh yes, yeah, definitely.
Yeah.
So now the telescope is slewing, so the stars are whipping by.
Here's a cool image. This is the first image that came off tonight, and so you can see lots of galaxies, very faint galaxies, stars. There's a very nice spiral galaxy here with disturbed arms. So you're going to observe, right?
You mean more than I am now?
Yes, right here.
You want me to actually
sit here? Yes.
The end of science as we know it. All right. Okay. Well, let's see. I'll just hit a few keys here.
Oh no way!
I just like to poke around. That's how I learn. You know. What should I do first?
Wait for him. When he says OK, you hit enter.
And that's it?
That's it, yes.
No. Okay.
Okay.
There it goes. There it is. And that sound was the shutter opening.
Oh, yeah, I heard that.
Now taking data.
Your first image in search of supernovae.
I hope I find it. That first night of the season, Nick and Chris and their team took 16 different snapshots of the sky. By the next night, now no longer observing from the telescope but from a control room in the nearby town, they had processed several of those images. And one of them, though sadly not mine, came up a winner.
So here we've got a big diffuse source of light, and it looks like it's probably a galaxy. And in both the images, there's apparently a little new light source just outside that galaxy. That looks like a supernova to me.
Great. This would be a really good candidate if we get a follow-up image to do spectroscopy. As a matter of fact, we don't need a follow-up image. This definitely is a supernova.
Supernovae are very rare events. The last one in our galaxy was 300 years ago. So it's only by staring at tens of thousands of galaxies at a time that the supernova hunters can hope for success. Once they've found one, there are only a few days before its explosion dies away. So there isn't much time for a large telescope like the Keck in Hawaii to get its spectrum. This spectrum not only confirms it's a Type 1a, but it also gives its age. The older the light, the more it's been stretched as space itself has expanded, and so the longer its wavelength, the more it's shifted toward the red. And because every Type 1a supernova explodes like a standard flashbulb, its brightness reveals how far away it is. And this is why both rival teams of astronomers were hunting so eagerly for Type 1a supernovae. By finding supernovae of different ages and measuring their distance, both groups hope to find the answer to one of astronomy's great questions. What is the ultimate fate of the universe? We met members of one team at Cerro Tololo. The other is based here at the Lawrence Berkeley Laboratory in California and is led by Saul Perlmutter. Both teams expected to measure how much the expansion of the universe has been slowing due to gravity, especially the gravity of all that recently discovered dark matter.
And we thought it was going to be a great project. We were going to find out whether the universe was going to last forever or not, or whether someday all the stuff in the universe, all the matter in the universe would slow the expansion down to the point that it would come to a halt and then collapse. And what we ended up with was, when we started looking at the data, it looked like there was very little mass in the universe. In fact, it wasn't slowing very much at all. And then as you really looked at the data, you started going, it's not only not slowing much at all, it's not even slowing, it's actually speeding up. And that was a real shock, because it was not part of the original description of our project when we were planning to use the telescopes. It was way better than that.
Instead of slowing down due to gravity, the expansion of the universe appeared to be speeding up, as if under the influence of some sort of anti-gravity. The rival team was coming to the same mind-boggling conclusion. Was it an exciting moment, or was it just puzzling and
puzzling and concerning, because it wasn't the expected result. So, I mean, we were expecting deceleration. So, really, the knot twist up in your stomach, saying, "Okay, let's go back and do this again. Make sure this is right." Yeah. And you go back through the numbers once again. You go back through the numbers yet again. Now you're starting to believe, well, we're onto something here. Wow. And the whole group, you know, we're distributed, and so the emails start coming in saying, geez, can this be right?
You don't want to come out with anything that's wrong, of course, in a scientific, a major scientific announcement. And so you're being so careful trying to check, well, maybe it's this, maybe it's that, and you're looking at every possible thing. Finally, we came to the conclusion, well, we have to come out and say it.
Were you all getting it right around the same time?
Yeah, we announced at the same time in 1998 at a conference in Santa Barbara. And both groups came out, and we sort of knew that the other team was going to announce the same thing, and I'm never sure how we knew that. But we sort of did.
Wait a minute. Were you pointing your telescope in their window and looking at their papers?
Us? No, we wouldn't do that. No.
The fact that both teams got the same result, I think, gave people a lot of confidence that it wasn't just some mistake that somebody had made in their calculation, because they knew the two teams would have loved to have been able to get the right answer and showed the other one it might have been wrong.
I have done it.
Not everyone was taken aback by the idea of a runaway universe. Michael Turner had actually predicted the possibility several years earlier, reviving an old idea of none other than Albert Einstein. Turner came up with a name for a force that could push the universe apart, dark energy. But its roots lay in one of Einstein's famous equations. The notion of dark energy was, as I understand it, something that he came up with and didn't really understand he had come up with it. How far off am I with that?
That catches a lot of it. I mean, in science, people were often confused. And so Einstein was confused about the expansion of the universe. His equations wanted a universe that expanded. And so he put in this fudge factor that canceled the attractive gravity of matter.
I mean, there's constant activity and chatter, and what is it all about?
Right. They're primarily monitoring health and safety. They're looking at telemetry. They're looking at temperatures and voltages of thousands of different components on the telescope and making sure they're all within their tolerances. They're looking at the heating on one side of the telescope when it's in the sun side. About once a week, we upload a whole week's worth of observations of what's supposed to be done that week to the telescope. And so if we find a supernova, for example, we usually have to find it by Tuesday, because Tuesday is the special day when they build the calendar for the next week. It's sort of funny. The light's been traveling for 11 billion years. It finally arrives, and it's got to arrive by Tuesday.
In March 2002, the Space Shuttle Columbia, on what was to turn out to be its last completed mission, installed a new camera on the Hubble, the Advanced Camera for Surveys.
This camera is much more sensitive to light, and it also has more area, so I have a better chance of finding a supernova every time I take an image in the sky.
Adam's plan was to look back with the new camera to supernovae exploding when the universe was young. He found some half dozen ranging in age back to 11 billion years ago. His hope was to find out if the universe has always been pushed apart by dark energy, or if it once had been reined in by the gravitational pull of dark matter.
We have roughly...
Adam Rees works closely with Mario Livio. Adam observes the universe. Mario comes up with theories about it.
Basically, you have the universe behaving something like this. At first, it is expanding against gravity, so think of it as if it's held back by some sort of a spring.
But it's getting bigger and bigger and bigger over millions, billions of years.
That's right.
And then at some point,
about 5 billion years ago, we think,
it stops slowing down And instead of collapsing,
over, yeah.
well, that's what we would expect it to do, get that big and then come back, right?
Well, even if not come back, but at least go slower and slower and slower.
Right.
Instead, it suddenly starts going faster and faster and faster.
And you found out when it started going faster and faster
That's
and faster?
right. We actually witnessed the transition from the more recent accelerated expansion to the earlier slowing expansion.
This turning point in the history of the universe came at about 5 billion years ago, when dark matter began losing its gravitational pull against dark energy's inexorable push.
You know, gravity decreases in proportion to distance. You know, if you double the distance, gravity becomes 4 times weaker.
Right.
This force that you get from the dark energy, when you make double the distance, the force becomes twice larger.
Oh, yeah.
We think it's a property actually of the vacuum, and so when there's more vacuum between you and a distant galaxy, there's more of this dark energy.
So
the force is bigger.
There is a factor of an increase in the amount of dark energy that has a factor on the speed.
Yes,
that's right.
It's a little bit like a built-in spring in the vacuum, and as something gets further away, there are more and more of these springs connected, and it's harder to compress. In fact, they're pushing more and more, and so the bigger the universe gets, dark matter is losing its pull on the universe. Dark energy is gaining its push.
It's always been there, right? The question that's now obsessing astronomers, including Michael Turner, is what dark energy might be.
So we just don't know what it is. If it is the like Einstein's cosmological constant, then it's just the energy of nothing. And according to quantum mechanics, nothing is not nothing. It's full of particles that are living on borrowed time and borrowed energy. We call
They pop into existence.
And then when the accountants come along, they disappear. And so if it's the energy of nothing, it's always been there. And then we're in for a very tough bit of history in the future, because the universe will keep speeding up and speeding up and speeding up, and things will get farther and farther away. And instead of the beautiful sky we have today with billions of galaxies, we'll only see a couple. It could be that it's just a phase we're going through, that something's out of whack and that the dark energy will dissipate. I think what you're starting to see is we don't know very much about it at all.
So all this stuff didn't fill us in that much.
We need help. We need some help.
Help may be on the way from a proposed new spacecraft expressly designed for supernova hunting. With a camera able to image thousands of supernovae at a time, the SNAP satellite would hugely increase the number of beacons out there measuring the universe's expansion. This might not only help find out what dark energy is, but also help answer what is perhaps the deepest question of all. Is there a reason why the universe turns out right now to be an almost perfect balance between the pull of dark matter and the push of dark energy? Or is the fact that dark energy didn't blow it apart in its infancy just a lucky accident? Maybe the Big Bang that turned out so well for us was just one big bang among many.
That if this burst of expansion happened here, there's no reason it wouldn't have happened here and there, and in the past and in the future.
Right. In the same universe.
In the same universe.
It was in what was the same, what started out as.
So now we need new language.
Yeah.
So the universe is the whole ball of wax, but they're different, disconnected pieces.
Right. It was like bubbles in a glass of champagne.
Exactly.
The champagne is the early, or a universe at any given time, or the multiverse. And each bubble is a new universe.
It's a new universe.
If this is our universe, where would the other universes be in this multiverse?
Thanks for passing me the universe here. We're actually kind of sloppy in astronomy when we talk about the universe, because what we usually mean is just the interior of this beach ball.
The part of the universe that we can observe is what we call the universe.
And that's, of course, strictly speaking, not true at all, because I don't have a single colleague who would entertain that space just ends here. You know, that there's a sign here saying space ends here. Mind the gap. We all believe that space goes on outside, and most of us believe that space actually goes on forever. and it's infinite, which means that there's another sphere like this, and in the middle of that, maybe there's another planet where people discuss their universe and can't see ours. And there's probably infinitely many of these.
If you have this ensemble of universes, there may be some basic things which are true for all of them, but there may be some quantities which are accidental in these different universes. Some of those universes will allow life to evolve and us to be here and speak about this, and some won't.
We said at the outset that our universe just got a whole lot weirder, dominated by matter we can't see and a force we can't feel. But maybe it's even weirder than that. Not only are we not at the center of our universe, maybe we're not even in the only universe, just in one in which dark matter and dark energy fought each other, at least when it mattered, back when the stuff we're made of was created.